The lecture is called Offsite and Onsite Structural Timber, and it's based on a case study which is the Longshaw Discovery Centre up near, sort of on the way to Hathersage. Has anyone been there on the Longshore Estate, National Trust? No? Okay. Do you know where the Fox House pub is? Yeah? It's just across the road in the Longshore Estate there. It's a project that I worked on at Alan Todd Architecture quite a few years ago. And I worked on the early design stages, and then the actual construction on site was run by Paul Tester, who you might know in the school. And I spoke to him yesterday. He said he has shown this project before, but he's never really interrogated the details, so it's not repeating that. However, it's not going. Bear with me a second. Okay, so that's a photograph of the building, and there's its location. It's not very good. Can you see that? Can you shut some blinds? Yeah. It's a bit better. I'll put the slides up on Mole anyway, so you can see the quality of them. So there's Sheffield. There's Longshore Estate. If you just zoom in, that's the Fox House Inn. So if you want to go out, the bus to Hathersage runs along this road here. You can get off at the Fox House Inn and go and have a look. And that's the kind of site location. So that's the building, this long barn. That's the Longshore Estate sort of house, which I think is where the National Trust tea rooms are. So it's well worth it. You know, it's a lovely place for a walk. You've got the Fox House if you want to go and have a drink or have lunch or something. So it's worth, it's worth getting the bus out and having a little trip to see it. The Discovery Centre itself is not really open to the public. It's more used for group bookings, but you can go and have a look at it from outside if you want. And these were our kind of design principles. We'll just go back to the site. You see the kind of location it's in. It's set within Gritstone moorland, within the National Trust. So it's a very sort of sensitive Peak District Park location. So light imprint on the ground. This was one of our important aspects. And because we were locating this building in a kind of greenfield site, we had to make the case to Peak Park that at the end of this building's life, you could easily remove it and just quickly repair, and you've not kind of permanently altered the landscape. Long-term flexibility and adaptability was important because the National Trust weren't entirely sure really what they were going to use it for, and they didn't want us to constrain their future use with the architecture. We wanted to use all the dimensions are all based on standard sheet sizes. So you'll see when we start looking at the project, it's a very timber building, but we wanted to not be wasting plywood, timber, OSB. So the whole building was dimensioned to plywood DIMS actually. So in one of the previous talks, I talked about dimensioning to brick DIMS, this sort of size. But here we were dimensioning to the sort of width of a sheet of plywood, which is 12-20 millimeters for a typical sort of UK plywood sheet. You can get 1300 wide and you can get 1250 wide plywood, but the standard is 1220, which comes from inches. It's a 4 foot, basically. So that's very important because we didn't want people endlessly trimming bits, slices off the edge of plywood. Now, some people play it safe and they would always dimension to allow for a little bit of trimming on the plywood. The benefit being that if the plywood has its corners damaged on the way to site, you can trim that off. But we said no, we said we don't want to do that. We don't want to be cutting the plywood, we don't want to be wasting it. You'll have to transport it to site carefully. Okay? Extensive use of timber as a renewable resource, and we had the aspiration to use local timber. We weren't terribly successful with that in the end, but that was the kind of agreement from the outset, that the National Trust would give us access to their managed forestry and we could have some timber from them. The orientation of the building maximizes solar gain, minimizes heat loss. If I just go back to the location, in this very, it's a very sort of open moorland setting. It's much colder out there than in the city, and it's much more exposed to rain and wind. I mean, just as an example, if you sort of look at the conditions outside here tonight, this morning, last night I went up to Ringinglow, which is, where is it? Here, sort of here, right about there. Up at Ringinglow, they've got that much snow, and it's not melted at all, just because it's a bit higher, it's colder, and it's like, it's complete it's full winter out there. It's not like in Sheffield it's all melted a bit, but they've just had snow upon snow. So we were very mindful of that this building, we didn't want to be heating it, we didn't want to waste energy heating it, so capture every bit of heat we could get from the sun. High levels of natural light and ventilation. So we wanted this building to be very passive. We wanted to generally try and daylight it. It's only normally used during the daylight hours, so the idea is we could minimize the electricity consumption, naturally ventilated. You'll see it's a very simple building, so we didn't feel the need for mechanical complex systems. Extensive use of untreated natural materials. So we were trying to use local timber if we could, and we didn't want to be slapping lots of chemicals on it and lots of coatings. If we could design the building so that it didn't need it, and there's, it's much lower impact if you can do that. As I said, locally sourced materials. That was one of the key aspirations. We weren't hugely successful anyway. Ground source heating. So we wanted to maximize the heat in the ground to provide the background heating for this building. Okay, so what I'll do, I'm going to talk you through, I'll give you some images and we'll talk through the building a little bit, and then we'll look at some of the details. So that is our location plan. It's slightly, I'm afraid that's slightly, there's the north arrow, so it's slightly changed direction. And this was our early proposal, and actually the location of this building did move a few times during the design phase. The brief for the building from the National Trust is, it's called a sort of discovery centre. It's basically a big open plan space. It's like a big classroom. It's got some toilets, and it's got a very light sort of kitchen facilities so that you could have a class out there, you could take a school group, you could run a meeting, and you could make cups of tea. That's kind of what it was about. And we won this from a competition. We had to submit some ideas to the National Trust, and we were selected to move forward with this, which we were delighted about because the competition was Prue Childs Architects and Robert Evans Vittori. So we managed to beat them. They were very unhappy about it. That's how it goes. Okay, so you might notice these are all hand drawings. This project was delivered entirely with hand drawings, which is kind of strange. But it was, what date's this drawing? Can't really read it. You know, I think we're probably talking about 10 or 12 years, 2003. So yeah, we're talking 12 years ago for this sort of initial scheme. Now, we were using CAD at that time, so it's not like we didn't have CAD, but we were using 2D CAD. And we made a decision in the office that because we were trying to work with natural materials, we were working with standard board dimensions, that we'd start the process by hand and see where that took us. And we just never broke out of it. So all of the details were done by hand. I think maybe it's partly because Paul Tester couldn't use Vectorworks at that point. He persisted on, you know, we had to do it by hand. But it did kind of have a nice relationship with the craft of making, that, you know, we drew everything sort of 1 to 5. It was all, you know, it was all very much related to the materials. And I think it, you know, it did kind of work. But obviously the problem drawing by hand is when you want to make a small alteration, it's very time consuming. So, you know, you look at this drawing here, if the client had said, for example, can you make it 1 meter shorter, then we'd have had to be scratching out and, you know, cutting the paper and resticking it, or scanning it into Photoshop and doing it in Photoshop, which is not really a very smart way of working. But anyway, we pursued by hand, and the methodology that we had in the office at that point was we had A3 trace sheets with a title block on, like this. That's what you're looking at, which was great because it meant you could do a drawing very, very rapidly, label it up, title it up, scan it or photocopy it, and it's done. And you could even do that on site, which was fantastic when you were having discussions with the contractors. You could draw a detail, label it up, take a photocopy, give it to them there and then. You know, not like, well, we'll get back to the office and we'll CAD it up and then we'll issue it next week via the online system. It was a very immediate process. So here's our initial design. It's a sort of big, you know, fairly big open space. It's got a little office, it's got some toilet facilities, and it's got a range of storage along the side there. And it has a sort of veranda around the edge and a covered terrace here for some outdoor activity. And this was our initial section. So we've got quite a sort of fancy kind of bowstring truss. A very simple. We were right from the beginning. We were going for this sort of vernacular barn, and that's the idea that we sold to the National Trust, and they really loved that. That we were kind of taking a peak barn typology and sort of playing with that a little bit. And at this stage, we had this large overhang over the balcony, which I'm glad we got rid of, because really that was not working with the typology of the barn. You know, barns don't have big overhangs like that. And these are some of our developed drawings. It has a lot of openings, a lot of windows, and right from the beginning we had these sliding shutters, which were important partly because at night there's nobody there, so we needed to secure these windows so that if somebody tried to vandalize it, it'd be quite difficult for them. It also protects it from the weather at night. So we all the way through we had these sliding screens. Some more fancy variants on the bowstring truss, getting quite complex there. And originally we had this very large skylight going all the way along the ridge, which we got rid of later. We actually didn't need it. It had loads of light. And again, it's not really a peak vernacular, that skylight. So that went. And this was a visualization which, because we were doing everything by hand, we sent that out actually to a local visualizer who did it for us. So that was a sort of visualization of how it would look. Very, very kind of timber shingles, timber cladding, with this big canopy. And the final building's fairly similar to this actually. we moved it. So that was the original location, which was facing sort of southwest, which would have been really good for capturing the sunlight. But planning were not happy with it. They felt that it would be quite visible from the main road, and they didn't really want that. They wanted it to be kind of hidden away. So we moved it down to here, right next to what's called the kitchen garden, but it's where the National Trust grow Christmas trees now, because they sell Christmas trees here. They cost a fortune, about 50 quid for a Christmas tree, but they make a lot of money from that. So we located it here, which I think it was okay. It probably, the orientation probably wasn't quite as good, but it was it was acceptable for us. Okay. Just go back to that actually. I think quite what I learned working at Alan Todd was the sort of quality of hand drawing and the sort of rapid, the way that you can rapidly produce a drawing. And Simon Geddy, who was at that point was the head of the Sheffield practice, he was really a sort of master of drawing, and I learned a lot of techniques from him. Just like how do you draw trees? How do you draw a road? Putting this thick black line around the building and sort of shading one side of the roof immediately makes it look like a pitched roof. The black line around it tells you it's a building. It's not not something on the floor. Always putting a north arrow on, always putting a scale bar. Just some really good techniques for hand drawing that communicate really well. And it's interesting that clients, they really warmed to these drawings. They really liked them, and sometimes in meetings we would draw with the client, and that that was a really sort of good way of working with them, which you can't really do in CAD. So there's this is one of the planning drawings. That's the final location. That's Longshaw House, and there's the Fox House in there. Okay. And these were our elevations, kind of as you've seen. Some very nice trees. We really worked hard on trees. I mean, we had a few, to be honest, we had a few trees on file, so if you're doing a section with a tree, and you could just put it under the trace and copy over it. And again, just a little bit of black. See, there's like a little bit of thick black line there, just to sort of indicate shadow. That's the visualization again. And one thing that we did improve upon is, I think this, you see we've got this gap between the head of the windows and the gutter, and it looks a bit, for me it was, at that point it was a bit kind of unclear what that was. You see when we actually built it that the steel mechanism, steel sliding mechanism for the sliding doors, and then the zinc gutters, they kind of really made a very clear set of lines that I think kind of articulated that distance between roof and the window head. So this was the final plan, drawing, and it's too small to read, but these dims are all 1230 millimeters. So that's our 1220 ply panel with 5 millimeters gap each side. Okay, and that's how the building was structured. So that 1230, it also equates in timber sizes to a sort of 4-foot plank of timber. Office, toilet, slightly reconfigured from the earlier scheme, and a lot of storage, and a big open plan room with lots of windows with sliding doors. So it's a very simple kind of layout. And then talk now a little bit about the structural development. So this was our original bowstring truss, whereby the tension forces in that roof are being restrained with tension cables here. Okay. And I think we felt it was kind of out of context with the building and the site. It was us trying to be clever. We're trying to do something quite fancy, in what was essentially a barn, a big barn, and it just felt kind of wrong. It felt like we were over complexifying the issue. Now, down the road, this was actually built afterwards. This is the Hopkins David Mellor Cafe. Anyone been here? Yeah, that's suggest. Really good building. And they've gone for a bowstring truss, and they've been quite clever about kind of pulling the bowstring up, so that the bowstring, the optimum position would be horizontal, but they've pulled it up like that. But again, that wasn't really our approach. We wanted this to be much simpler than that. And that's actually the final section that we built. And I'm going to do a few drawings now to explain it, because what happened with this, although it looks very simple, and it looks like a much simpler, I would say it's a much simpler approach than that, but structurally it was actually very complex to achieve this. And I'll do some drawing. The structural engineers were Arabs, and we worked with, I think Greg Hardy was one of the engineers. Luckily for us, Arabs took it on board as a research project, because basically no way did their fee cover the kind of structural research and application that went into this, because the fee was fairly modest. But they said, well, okay, we'll take a loss on this job because we want to develop this kind of timber structural research. Otherwise, we couldn't have done it. Most engineers would have just looked at that and said, that doesn't stand up, you can't do it. Okay, so I'll go now to some drawing. Okay. So, we just talk about that kind of structural principle first. So we've got a building which sits off the ground. So we've got some big timber bearers lifting this building off the ground, and we've got a few concrete. I think they were pads actually in the ground, and we've got some galvanized steel brackets in there just to lift that timber off the ground so it's not getting wet. Okay, and I think, could be wrong, but I think we cantilevered out, so that the edge of the building I think is slightly cantilevered from the supports. I could be wrong on that. And this is what we wanted. We wanted our timber walls like that, and we wanted our roof kind of like that. And what we didn't want was that. So we didn't want to tie that. Now the problem there is, as I'm sure you can imagine, you've got weight in this roof, and bearing in mind it's now got 1.5 feet of snow on it, probably. You've got a reasonable amount of weight on that, and that weight pushes down, and that weight then gets transferred through the rafters, and that then tries to push the walls apart. Okay, which is why normally this tension member here does a fantastic job of just keeping those walls in place. But we didn't want that. Now, if I just draw over here, if you've got a shorter building, then what you can do, like in a traditional Sheffield terrace, is you can have purlins, big bits of timber that span from the end walls, which would be made of masonry or brick or something. And that allows you in a typical Sheffield terrace, some of you probably live in one like this, to have an open roof space like that, okay? Because the load is actually being taken on these purlins and transferred into the cross walls. But on our barn here, oops, we're kind of, we're that long. So the purlins that we would have needed would have been enormous. We just couldn't do it. So no way. So that was our kind of challenge for Arabs. Okay. Now there are a few other aspects structurally here. We wanted to maximize off-site fabrication because it's quite an exposed location. You get a lot of weather out there. We wanted to minimize time on site, which is always a good thing, but particularly in this location. The National Trust, they didn't want a building site for 14 months. They wanted it done quickly in the summer. So one of our initial ideas was that we would prefabricate the wall and the roof structure. So if I just draw quickly, the walls here would be prefabricated structural insulated timber panels. Okay, well, people call them SIPs, but this was not a product. These were manufactured in a yard, bespoke to our dimensions. And I'll draw those in more detail, but basically they consisted of something like this: timber bearers, like that, with plywood fixed on both sides, full of sheep's wool insulation, plywood. So they would come to site ready-made. Which meant we weren't doing all that kind of joinery work on site. But equally, it's not a product. We weren't buying some off-the-shelf product that we had to design our building to. We could have whatever we wanted, but the joiners could make it in a nice dry factory and then bring them in. Okay, and it was the same principle in the roof. Where again it was a kind of a panelized system, something like this. Not quite sure what the detail was up here. But everything would come to site and would be kind of bolted together on site. Okay, so that's a bit crude, but there we are. That's the kind of principle. Now, to go back to this structural problem, the way Arabs made it work is, if I just draw a 3D view here, kind of like that. So there's our building, and we have got a wall inside it. Like that. So there is a wall here, because we've got that office and that toilet block. We've got a bit of a cross wall there, which helps us. But basically what Arabs had to do was they had to say, well, this whole roof has to become a diaphragm structure. So all of that becomes a diaphragm. And what that means is that whole roof becomes a kind of stiff, rigid element that can transfer lateral forces. So that if I put a force in the middle of it here, rather than just transferring all of that force outwards, that whole roof acts as a kind of big beam, and it will transfer the loads laterally into the side walls here. And then our end walls are very, very strong to take that load. And it's funny because as the architects, Arabs were saying how complex this was, and we just didn't get it. We just said, well, it's just a simple barn, isn't it? But they were saying, well, no, because you've given us no means of taking this horizontal load out, and then you've told us we can't have any steel. So the only steel in this building is for connections. The rest of it is timber. If we could have allowed them to have steel, they could have put big steel members up in this roof to take those loads out. And then also, to make it even more complex, this roof has to be made of panels like this. So we're not allowing the engineers to work with large spans of timber. We're only giving them these sort of 12, 30 by probably 3 meter panels, and they had to work with joining those together. Okay, so is that kind of clear in terms of the structure? What's going on? Any questions on that? Yeah.
The diagram is basically like a truss, two trusses on.
It's not really like a truss. It's like a big, rigid. Let me find something to use as an example. I suppose use that. That was the roof. The diaphragm. It's so rigid that if I put a load here, in a normal rafter situation, if I put a load here, it can only transfer the load straight down the rafter. But in a diaphragm, because it acts as a beam, if I put the load here, it can transfer that load laterally into the ends. So it is like a truss, but I suppose because it's all sheathed in plywood, it's it's like a shear wall, yeah, but in the plane of the roof.
Was the moment then over the top?
Was the what, sorry?
Was the moment taken over the top?
No. Well, yes, I guess there is, because it's a rigid joint here.
And that's all induced kind of lateral portalizing.
Well, that's kind of helping because it's slightly portalizing. So because these joints are not pure, in a pure pin joint situation, they can't transfer a moment. I think that's what you're getting at. I don't really know, but I guess because of the nature of the way these timbers were bolted together, there probably is a certain amount of moment resistance in those joints. I'm not quite sure whether they calculated those in or not. But I mean, you're right, because that would be the other way of doing it. If you took a roof like that, and if that joint was so strong in terms of the moment, then it simply won't bend out. Maybe, I don't know. Maybe they were calculating in multiple factors to achieve this sort of rigidity. Yeah. Okay. Let's just go back to the presentation, to the slides, and then we'll come back and look at some of the constructional details in a moment. So that's the final plan, just looking a bit closer. And you can probably just about make up, we've got these double timber members where we join the panels together. I'll draw that in a moment. That was the final section. You see, I was talking about that relationship between the gutter and the head of the sliding door. We kind of shrunk that down, and you'll see in a moment the sort of expression that we made of that. These are some of the details. So I'm going to draw some of these, so I'll just go past these quite quickly. We'll look at some images of the building, then we'll come back. The cladding was large, and I think this is where we failed. We wanted to use local larch, and I think the National Trust couldn't provide it in the end. But it's untreated larch, and we just worked quite carefully with the gaps so that we were achieving good ventilation behind those boards, but we didn't want to see through them. Okay, so that's why we have this sort of detail, and just chamfering off that sharp bit just in an attempt so that we don't end up with little broken edges there. Okay. And this was the kind of principle of our wall. The rain screen cladding deflects the rain. We keep the moisture in the building, and we allow the heat in the building to push that moisture out through the wall. I'm going to draw this again. And we have a breather membrane on the outside just to keep any moisture out, just in case. And then we ventilate by opening the windows, effectively. The windows have trickle vents as well, but for rapid ventilation, you just open the windows. Very, very simple. And in that kind of construction, you've got to be very careful about condensation, because what you don't want, I'll just go back, you don't want moisture in the building from people's breath. You don't want that to condense in the insulation. Okay, the sheep's wool insulation is pretty good with moisture, but it's not going to survive if you're allowing water to condense in there. So what we did is we did some dew point assessment. We actually used I think it was the Thermofleece, the sheep wool company, the manufacturer did these calcs for us just to check. And I've got closer. What we've got is you've got the inside of the building here and the outside here. So it's reversed from the previous slide. Okay. And the red line is the temperature in that wall construction. So inside the building it's about 20 degrees C, and in this analysis outside it's about 5 degrees. And the dew point is based on the materials. This is the temperature that they know that you could get condensation. Okay. So what you need to make sure is that your temperature doesn't, well, where it drops below the dew point is where you're happy to have condensation. So we don't want condensation inside the building. We don't want condensation in the insulation. We're happy to have condensation on the outside of the building, okay, or in the ventilated zone. And what this showed us is that we were okay. If I just go back to the key there, 6 and 7 is the Thermofleece insulation. We were okay because the dew point, we were hitting that outside of our insulation. So any condensation, we were pretty happy would occur outside here. Okay. Yeah, that's right. What we did in the end, if I go back to this drawing, you see here we've got a vapor barrier. So a sheet of plastic stapled on the inside. We didn't want that. If we could avoid it, we didn't want that plastic. So what this is demonstrating is actually, this is simulating the condition without that vapor barrier. And what we're looking at is the fact that we've got plywood on the inside, which is quite impervious to vapor. We were testing, can we remove that vapor barrier? And this demonstrated to us that we could. And we submitted these to building control, and they were happy with this. Okay. This is just some of the plywood furniture that we built inside. Everything was built out of birch ply. So just to understand, when we talk about plywood, there are very, very many different types of plywood. Birch ply is a birch-faced ply. It's birch throughout. Gives you a much better quality of finish. It's not a sort of marine ply or a building grade ply. It's a better quality. So here we are on site. Excuse me. These are our prefabricated panels, and they come to site with windows in as necessary. They're all the right size, and we craned them in, and it went up. These panels went up in a few days. It was fantastic, really, really quick. And then we're putting the roof on. So here you can see Not very clear for you, is it? Okay, but you can just make out this is the top of those panels. They're joined together. They've got a plywood panel on the top, and then we're putting the roof structure on the top. And in fact, yeah, sorry, I've missold that. The roof, we wanted that roof to be made out of the prefabricated panels, and Arabs, in the end, they couldn't make it work. Sorry, I've forgotten about that. So fairly last minute, we did have to go back to a more normal kind of timber structure in the roof, but still working as this diaphragm. There's our breather membrane stapled on the outside of the ply, and a roofing sarking membrane just nailed onto the roof plywood, ready for the next layer. And what you might notice, they're getting that on quickly, so they're putting that sarking felt on before they finish the roof, just in case it rains, basically. You know, get this building dry as soon as we can. There's our one of the connections for the one of the columns at the front. That's our larch boarding, which you might notice they didn't chamfer off as we wanted. And we had some issues with that because the fact that they hadn't chamfered off meant that sometimes those little sharp arises got knocked off. Now when we're putting larch boards, we don't want one of them to be slightly wavy. They need to be quite flat. So we had some issues on that. And these are our shingles ready to go on the roof. I think they were cedar shingles. And here we are inside. So we've got a timber floor construction. We've got a slightly more traditional closed cell insulation in the floor, and this is our underfloor heating pipe going in. And then we screed it in between that up to the joists. That's the underfloor heating. That's the roof with all the sheep's wool in it. And this is our diaphragm. The fact that we've put all of these timber noggins between the rafters to stiffen this whole roof structure up. And this is the first layer of plywood going in. And you'll see when I draw the details later, we had 2 layers of plywood because we wanted to create a wiring zone inside. I'll draw that. And there's our plywood, all uncut, all straight off the lorry. We're not cutting it down. And that's a final view as it was completed, with the shutters closed. And a few details there. So here we've got one of the shutters. This is actually on one of the gable ends. And this is our expressed galvanized sliding gear for the shutters. Now you can imagine those shutters, because they have a galvanized steel frame and then they've got the cladding, each of these doors probably weighs about half a ton, so they're quite heavy. So the sliding gear, the sliding channel it's very heavy duty equipment. That's the expressed zinc gutter. Stainless steel handles. That's the galvanized frame to one of the more conventional doors, I think. No, it might be a sliding door. Normal, just fairly traditional aluminium windows. I think these were in an anodized finish. Okay, and that's just a detail of the timber. We fixed the cladding on with a recessed bolt fixing, like that. So just had to pre-drill a little hole, and that makes it nice and neat. That was all drawn, so we didn't want people making it up on site. We told them exactly where to fix it, which on a building like this is quite important. So there's the relationship of the gutter to that sliding mechanism, and it has a little profile over the top just to keep the rain off it, which I'll draw in a minute. I think that's the detail. It's probably the detail above a window before the window's actually been fitted. So with a little, I think that's, I'm not sure if it's zinc or aluminium, might be aluminium. Little flashing just to throw the rain off the top of the window. Okay. Just a few light fittings. And that's the view inside. So this is all birch ply with a, it was actually I think it might have been an oak floor, can't quite remember. Stainless steel electrics using that wiring zone behind to hide all the wiring. The toilet was even done in birch ply. And then I've got just a few images of it more recently. So this is an image just as it was built. And if you look at the sort of colour of the timber, a lot of people talk about, with timber, about this sort of hat. You know, have a big hat, big wide hat to throw the rain off. Now, there's good reason for doing that, but that's not the peak barn vernacular, so we didn't want to do that. You know, we didn't want this thing to look like a Swiss vernacular. We wanted it to look like a Peak District barn. So we didn't do that, and we accepted that there would be some kind of differential weathering down that face, but you know, that's kind of the nature of the Peak District. So here's a more recent photo, and you can see that we have weathered here. It's gone much darker, and there's a bit of differential weathering you just make out there where it's not darkened quite as much. But you know, we think that's fine. That's just the sort of natural aging and weathering of a timber building. It's not a sort of defect. You know, it's sort of greyed. I think it's a much more kind of natural colour now, the timber. The zinc gutters are fantastic. They're really robust. They can keep snow in them. You can even, you know, it's not great, but you can have contractors leaning ladders against them and they don't crack and break, whereas plastic gutters just break all the time. I've persuaded many clients to use zinc gutters on the basis of cost efficiency over time, and a lot of them have gone for that because it's much cheaper to put plastic gutters in, but you'll end up replacing them every 5 years, whereas the zinc ones will be there for 20 years or more. And if you're using it from this is a product called Lindab, and they use a lot of recycled material. There's the corner detail. You don't really see it, but there's quite a tricky junction there where the down pipe had to come through that flashing over the sliding mechanism. And here we had slightly unfortunate, we had a failed board here which had to be replaced. That's the sliding shutters. So here's our galvanized rail with the flashing over the top, and then our zinc gutter. Little sort of flash of galvanized steel around the edge of the shutters. And I think we were really pleased with the way that turned out. That relationship, I think, just worked very nicely. Okay, so I'm going to just do a few drawings now to look at some of those details. So I'm going to start looking at that, looking at the eaves detail. So I'll start with those timber bearers. Okay. So this is one of our wall panels. So we've got plywood on the outside, and we've got plywood on the inside, and both of those sheets of plywood they're never going to be seen. So for those we used a building grade plywood, which is, you know, good plywood, resistant to moisture, but it's not got the quality of finish that we would get from the birch plywood. So that's one of our typical panels, and then inside of that is stuffed full of the thermofleece, the sheep's wool insulation. Okay. Then on top of that we've got a wall plate, and this is just a sort of long length of timber which is just holding everything together, ready to take the roof structure. And then our rafters come off that wall plate, and they were fixed with a galvanized steel bracket, something like that. So that's our basic kind of structure. Then the roof is covered with plywood. Now, normally in the UK, you don't have to do that. On a more normal site in the UK, you wouldn't do that. You would, if you forget that plywood, you would put a roofing membrane, breathable membrane on, and then you could fix your battens. And then onto those battens you could put your slates or tiles or shingles or whatever your roof covering is. Okay, but in Scotland and in our location, because of the sort of adverse weather conditions, we sheathed it in ply, and also Arabs needed that plywood to act as this to help this diaphragm out. So yeah, so we covered the entire roof in plywood like that. And there's little bits of, we had to fill in little bits of plywood like this. So that went up, and as I said, as soon as they could, the roofing felt went on. And at that stage, that's just left flapping, ready for the gutter. The breather membrane was stapled to the outside. And really, that breather membrane there is just about protecting the building during construction. It's not really needed, but it keeps it all dry. Then we have our gutter, our zinc gutter is sitting kind of like this. And that zinc gutter comes with brackets like this that we fix back. We just secure those back to the timber. The roofing felt just laps into the gutter. Okay. Then we've got a ventilated zone on the outside here, which, because we've got horizontal boarding, we needed to put vertical battens Next, so vertical battens are nailed onto here, and this is typically done with just with a nail gun. It's incredibly quick with a compressed air nail gun. You just and it's fixed. It's fantastic. Not, you know, if I'm doing stuff at home, I'll be there, you know, with my screwing. Like, that's all they do. And then the larch cladding goes on. Now again, with the larch cladding, the contractors wanted to nail it on, and there's good reason for that, because you can secret nail it. So with a nail gun and the right nail, you fire it, and the nail disappears beyond the face of the timber, and the timber kind of closes up around it. So, you know, that is a really good approach. That can look very neat. But we wanted this slightly more expressed fitting. I think partly we were copying the Chipperfield Henley Rowing Museum. They'd used those expressed fittings, so we wanted them as well, probably. But, you know, the contractors were saying, what, you know, why are we doing all these recessed fittings and buying all these bolts? We can just nail it on. But I think, you know, I think it worked. I think it kind of looked good in the end. Okay. So there's our basic wall. I'll finish the roof and then we'll look inside. So we've then got our shingles, and with any kind of layered roof, you often have a little kicking batten at the bottom, just to kick that, just to stop that bottom layer kind of flopping down into the gutter. And you don't normally need to worry about that, because the roofers will know what they're doing. Okay. So that's like that. Then our shingles are then kind of lapped like this. Sorry, that's not drawing that terribly well. The shingles lap over, and though the shingles they are just nailed in place. Okay, so you've got multiple defence layers. The rain will hit the shingles and it will drain off into the gutter. If anything gets blown underneath, or if you have a shingle that gets blown off, the roofing felt will deal with that and will disperse that rain eventually into the gutter as well. On the outside of the building, we've got a little ventilated zone behind the cladding, so that any moisture that's hanging about will get dried out. So let's just finish the inside. So the roof, the underside of the roof, the ceiling was clad in 18mm birch ply, which is it is acting structurally, but it's also acting as the internal finish. So that's the birch ply. And then we created our wiring zone. So we then put the internal birch ply cladding here. Which, I mean, you could argue that that was kind of unnecessary, actually. But I suppose the other thing it did allow us, because the wall panels were coming to site and built on, you know, erected on site in the rain outside, probably the prospect of trying to keep this internal face undamaged was probably very, very difficult. And what this allowed us to do, I suppose, was to get that building up, and then we could keep the internal face, the internal finish as a much kind of neater trade once the building was watertight. So there's our there's our internal ply, and that was just fixed back to horizontal battens. And I think that probably was just nailed, not entirely sure, but I think it was. And what that allows us to do is when we needed to put, say, a socket in, we could sink a back box, and the wiring can run in that wiring zone, which worked quite well. Then in the roof, what we saw on one of those images is in between all of these rafters, we've got these very closely spaced noggins, chunks of wood, chunks of timber, which are helping to strengthen that whole roof structure. That's our ply. And then this was stuffed with insulation. Okay. Right. Can anyone see? I had a chat to Paul about this yesterday, and we were talking about ways in which this could be improved. You know, this is 10 years old, this building. Can anyone see, in terms of sort of energy performance, a problem with this build-up, this construction? Don't worry, I hadn't noticed it either until Paul told me yesterday. Yeah? Yeah, exactly. Yeah. So by modern standards, you wouldn't really class this as a very, very highly insulated wall, because although we've got loads of insulation, we have a complete cold bridge here through the timber. Now, although it's timber, timber doesn't conduct heat that well, but by modern standards, that would be considered a cold bridge. So it would be a loss of heat, loss of energy. And the way to improve that, probably what we would have done if we were doing it again, would have been to probably in here put a layer of a sort of insulating wood board product, like a Pavatherm is a sort of wood chip board, which is quite strong, but also it insulates. So probably adding a layer like that would be a good idea, just to minimize those cold bridges. Okay, and it's the same in the roof. If you look here, we've got a cold bridge straight through. Now it's not an issue really in terms of we're unlikely to get condensation forming, because it's a well ventilated building, but we are losing heat through that. Okay. Any questions on that? Yeah.
How would a non-insulate the rafters?
With a little galvanized bracket, little angle plate. Yeah. So if I draw it, let me draw that in sort of plan view. That's a rafter. I think, from memory, I think you could just, on a more conventional construction, you could just angle nail that. So you could put two very long nails in at an angle, or screws. But I think because of the structural performance that we needed, I think Arup specified some little galvanized steel brackets. I'm not sure if they were on both sides or only one side, but I think they were quite worried about this connection being too weak So, it does increase the amount of steel work we've got, but I suppose, we were achieving a sort of predominantly timber building, so that was sort of acceptable. Okay, let's put that socket in there. Anyone else got any questions on it? Okay. Now, what I'm going to do now is just quickly look at the window detail, and I'll just trace over this one for speed, I think. So in our window condition, and I'm just cheating, I've got a drawing here in front of me. We kept one board, one of the large boards gap between the underside of the gutter and the head of the sliding rail. And then we've got the flashing, which is, yes, aluminium flashing, it says here. So we've got that little aluminium flashing. Okay, and see what Paul has done here is he's rested that on a timber piece. He's obviously worried about that aluminium flashing getting bent or getting snow on it and sort of getting all floppy. So there's a timber piece in there and he's put a little drip on that, so that if any rain does come underneath it, it will drip off, it won't track back. Okay, then we've got there's a substantial steel bracket. There. Okay, so that's a steel bracket which is taking the load of that sliding screen, and what we've done is, there's extra timbers in there, so we couldn't just fix that steelwork back to the plywood, so in those locations we've got extra timber bearers in the wall, like that. Okay, and these were fixed back into the timber. I'm not quite sure whether that was with some, it might have been with some enormous coach bolts with a kind of big aggressive screw thread. I'm not sure, or they may have been bolted all the way through the timber strength. I'm not sure, it doesn't tell me on the detail here. And then fixed onto that is our galvanized steel sliding mechanism, which is a product. So it's an off-the-shelf product. It's not something that we were designing. Now on here it suggests that there's a sliding mechanism on the inside. Yeah, that's right. So this again is all a product. You've got some seriously heavy-duty wheels inside this with stainless steel rollers, bearings, all greased. It's a product. Okay, and that comes down, and then our sliding door sits within this galvanized steel frame. So we've got a substantial bit of steel there to make that door work. And I'll go back to the pictures at the end. You've then got an express clamp on the outside, which kind of helps to fix this thing back, and it also expresses. We've got these. You'll see we've got these sort of fixings every meter or so on that sliding channel. Then our larch cladding sits in here on the doors, and it was all lined up. And that was all lined up with the cladding levels on the building. Okay. And inside of that, there's just some timber bearers there, just to take that cladding. Okay. And then the door head under here, we've got a similar principle where we've got a piece of timber with that aluminium flashing on it, and the breather membrane laps onto that. Our plywood continues behind all of that as before. And what the detail at the door head or the window head is quite a nice one, is that that timber bearer for the flashing also becomes the underside of the window reveal. And the window, in fact, looking at this, these look like timber windows with an aluminium cladding on the outside. Okay. And there's a timber boarding on the inside as well. There's our window. So what I was saying about that window is it looks, from the way it's drawn here, that it's actually a timber window, and you can get timber windows now where they just put a little aluminium cladding on the outside just to protect the timber. I mean, modern timber windows are very good, and they typically, a painted timber window will come with a 10-year guarantee on the paint. So, go back in time a little while ago, you would have always specified aluminium faced windows for longevity. But nowadays, timber windows are so good that you could always, in terms of low impact materials, you might argue that a timber window is better actually than an aluminium one. You won't need to maintain it for at least 10 years, and they are much cheaper. So it's worth bearing in mind when you get out into practice that sometimes timber windows are quite a good option. Right, just finish this off. So that's all like that, and then it looks like they've squeezed, oops, wrong place, they've squeezed in a board in there. So I just do that. So there's, it kind of works, doesn't it? That's our window detail. So what you see, as you look through, you've got these, I think they were larch reveals. We've sort of hidden that slightly messy junction of the window, because in reality that window will be fixed in and there'll be lots of mastic and sealant and packers in there. So we've hidden all of that. I mean, it's not, I've drawn it quite crudely. These were all probably sort of 5mm gaps to make it all nice and neat. We don't need a drip on the inside because it's not raining inside the building. But we've got this nice sort of reveal all the way round. There's our insulation. We've got loads of cold bridging through this. Okay. I mean, it's funny because back 10, 12 years ago, people didn't really consider that timber cold bridge to be such an issue. And I'm sure with this building, building control looked at it and said, well, you've got 200 millimeters of good insulation in those walls. You've done well. Nowadays, they would say, well, you've got cold bridges. You need to address that, which is good. We're minimising the energy loss. So, any questions on that window detail?
How would you address the cold bridge in that area?
Here. I think again, it would be. I think again you would add another layer. So I think you would add a layer there of either of 50mm insulation, but probably one of these Pavatherm boards. The great thing about those is you can just fix it across the whole wall. Then we would have. So let's say that is Pavatherm. Just write that on there. So if we fix that on, we then could have fixed our internal ply directly to the Pavatherm. So we would have emitted all those battens, which is a bit of effort. Now, okay, you might say you've not got a wiring zone, but to be honest, this wiring zone, it was not a zone that you could retrofit. So possibly, well, we would have had choices here. We could have allowed the contractors to channel out in the Pavatherm, which would be pretty easy because it's quite soft. So wherever they needed cables, they could dig out. Or, what might have been a better solution in terms of flexibility would have been to say, let's just have galvanized sockets. Expressed face-fixed galvanized sockets into galvanized trunking. Or, it looks neat, looks really good. And then if you need to change the wiring at a later date, there it is. That probably would be a better solution to be honest. Any other questions? Yeah. I'll just see if there's any more questions.
Oh, okay.
Yeah.
I don't know. The question was how the door. Does the door sit? It doesn't slide in and become flush with the wall at all.
No, it sits in front.
Yeah.
Sits in front. Yeah. Any more questions? Yeah. No, you probably did miss that. I'll go back to that drawing in a minute. We've demonstrated, because you've got heat inside the building, it's cold outside, but because we've got this sheet of plywood, which is very impervious to moisture, we demonstrated that the moisture in here, most of it would be retained in the building. Any moisture that does get into the wall buildup, we demonstrated that it would only condense here, outside. So we were okay with that. I mean, we just didn't want to cover this whole building in plastic on the inside, so we worked quite hard with that. Okay, I'll go back to the pictures. I mean, the other thing it doesn't really show here is we fire engineered the design so that, because we didn't want to have excess fire escapes and lots of signage, we did a little calculation to demonstrate that people could get out very, very quickly, rather than just the standard sort of building control. So let's go through the images, if you will. Sorry about my computer. So there's our wall. No, that's a special wall at the end. Forget that. That's not the normal construction. There's the roof with all the insulation. You probably can't see it on the screen there. You can just make out there's a little galvanised bracket there fixing the timber together. I think they were just off the shelf. Just these sort of products you can buy, which you can nail gun, I think. That's inside. So there is, yeah, the shutters are in front. And of course the sliding mechanism runs all the way along. And those little things there are those, you can't really see them, can you? Those are the express brackets that hold that mechanism. That's our window, which it is a timber window. It looks aluminium, but that's just painted timber, and it has a little aluminium cladding sill on it just to protect that vulnerable part. Yeah, that's the little galvanized frame around the sliding doors. And that there is that flashing over the window opening that I was drawing a minute ago, and we've just brought it through a little, but I guess just to make sure that there's no rain sort of trickling around the edge. So we've just extended that a little bit. That's the aluminium flashing over the top of the sliding channel, and it's sat on that timber bearer to try and keep it nice and level, although you can see even there's a little bit of sort of unevenness in it. That will be a window. That's where the window will go in. That's the aluminium sheet over the top, sitting on a piece of timber, and you can see it's sort of cut. It's cut into the board there. Yeah, and that's right. The channel, the sliding mechanism runs all the way along the building. So we didn't want to just sort of stop and start it, but it's an element. So we've got this very timber building. It's got this sort of grey zinc gutter, and then it's got this grey steel sliding channel. And then you just get a few other little flashes of steel work, and that's it. Very kind of restrained. That's the clamp holding the mechanism. And you can just about see it's a channel. So the sliding gear sits inside that. You have to put it in from the end. Okay, that's just the decking. So the internal plywood, and yeah, flush sockets, but really, maybe we should have done that as expressed sockets there. And there, quite a good view of a window there. So this idea of the window reveal that frames all the way around the window from outside to in, just neatens it off. Timber window, that's the trickle vent. Just about make it. There's a little trickle vent there. Architects get very upset about trickle vents because you see them. There are windows. Some of the more expensive windows have a hidden trickle vent. But I find as an architect you kind of mature a bit, and you worry. There are bigger issues in life than whether you can see a trickle vent. But when I was 25, that was very important. That's a view of it from the outside. Yeah, so there's the idea. You've got that continuous strip there, and then the gutter is this other continuous line. It's also this express sliding mechanism is picking up on some of the sort of agricultural typology in the Peak District, where you have a lot of sliding doors on barns. And there we are. I think for a building that's 10 years old, made of timber, it's looking pretty good. It's kind of maturing. It's getting a bit darker, but it's lasted well. The National Trust were worried about the shingles on the roof. They wanted it in. I think they wanted us to do it in zinc, But you know, we said no, it's fine. Shingles will last. You'll have to replace them in 20 years, but 20-year lifespan is okay. And then you give some. You're going to employ a local roofer to do a bit of roof work. That's okay. Sliding door, yeah, it's sat proud. Just see the little rubber stop there, so it doesn't bang into the one next to it. That's it. Any questions before we go? Yeah.
Is there an easy way to calculate dew points?
Yeah, they'll do it for you. Yeah. All of the all of the big insulation manufacturers offer a calculation service. So generally, you can ring any of them up and say, right, here's my wall. How much insulation do I need? Can you check my dew point for me? If you're doing a flat roof with tapered insulation, Kingspan will do your full design. They'll come back with full CAD information of it. And it's kind of right because they're the experts. As architects, do you want to be do you want to learn how to do dew point calculations? Probably not. And if you don't do it for 3 years, you'll forget anyway. So, I'm quite happy to let the experts use their expertise and help us out. And they do it free of charge because they're likely to sell some product out of it. It's the same for it's quite a key one when you're doing ground floor insulation. Get them to look at it for you because of the thermal mass of the ground, you often don't actually need any insulation below a building, and you could be wasting money. You could put a lot of insulation under your building, and it's not really doing a lot. And your client would not be very happy to find out they've spent £20,000 on something that's kind of wasted. All right, great. Thanks, everyone.